Hi, good morning, everybody. Welcome to the Waves on a String Lab. So we're going to be making waves on a string. And so we need to define a couple things about a wave. So first of all, if I just draw a wave like this, the distance between any two crests on a wave is referred to as a wavelength. And we use the Greek letter lambda to symbolize wavelength. And the reason why we use lambda is because we ran out of L. We use L for everything else. Okay, now the other thing that we talk about is we talk about what's called the frequency. Now, when a wave moves up and down, so the time it takes for the wave to go up and down like that would be one period. But these waves are waving so fast that these periods are just too hard to measure. So we talked about period before. So what we talk about is instead of the number of seconds per cycle, which is a period, the number of seconds in one cycle, we're going to talk about the frequency, which is the number of cycles per second. And this is measured in a special unit we call hertz. So if you've ever heard of hertz, that's frequency. Now the speed of a wave is given by the frequency multiplied by the wavelength. How far it moves and how often it moves. So that's our standard wave. Now we're going to take this wave and put it on a string. Anybody need me to keep this up for a second? Anybody got this far? Okay. So what we're going to do is we have a frequency generator that we're going to attach to a string, and then that string is going to vibrate between one point, and we're going to have a pulley over here with a mass hanging down on the end. Now I got to be careful. This is going to be capital M here, so that's a capital letter. And what we're going to refer to as the vibrating length of this string, capital letter L, is the vibrating length. Now the thing is that with any kind of wave on a string, I can only fit certain patterns, because this has to be at the middle and this other end has to be at the middle, or in places we call nodes. And what will happen is this wave will vibrate up and down like this, because the two ends of the wave are fixed. So if I look at it, I can have a wave with one loop, or a wave with two loops, or a wave with three loops, but I can't have a wave with 1.5 loops, or 3 3/4 loops, or pi loops, or whatever. It has to be some number. So we're going to call that number n. Now for this first wave, the entire length of this thing only has half of a wave. So this has halfway. So L equals 1/2 of a wavelength, because I only have 1/2 of a wave. For n equals 2, how much of a wave do we have?
One.
Yeah, we've got 1. we've got the whole wavelength. So L equals 1 wavelength. How about for n equals 3, what do we have?
1.5.
For n equals 3, how much of a wave do we have?
1.5.
Yeah, we have 1.5 waves. So for n equals 3, we have 1.5 waves. Okay. Now I'd like to know how many waves we would have for any n. Okay, so this is n equals 3, n equals 2, and n equals 1. Let's say n waves. How much would it be? Okay, well, you can type in chat how much would it be. So how many wavelengths would it be for n waves? And so type in chat, people, type in chat. Meanwhile, I'm going to help you out by changing these numbers. First of all, this 1.5, I'm going to change to 3/2. Okay, 3/2 of a wavelength. And even though it might look a little silly here, for this one, I'm going to make it 2/2 of a wavelength. Now, one is 2/2, so do it like that. So there you go. So it's just half of n. So whatever the n is, it's n/2 of a wavelength for any n that you have. Okay, so for any n you have, the length of the string will be n/2 times the wavelength. And those are the only ones that are allowed. So what we're going to be doing is we're going to be adjusting these frequencies. And we're only going to get certain ones because of the length of the string. So if I look at what happens here, and I use our formula, the velocity of the string is going to be set. So that's equal to frequency times lambda. So I'm going to say that the frequency then is equal to the velocity divided by the wavelength. Or if I solve this, what I get is the frequency is equal to n times velocity divided by 2L. Just a little bit of algebra there to get this. Now, that's the frequency for any particular n value. The frequency for any particular n value is equal to that n value multiplied by frequency divided by twice the length, the vibrating length of the string. So what we do is we're going to say, okay, we're going to call the fundamental frequency is F1. The fundamental frequency is F1, and that's simply equal to this, velocity divided by 2L. So it's this fundamental frequency that we're going to be looking for, because all other frequencies are going to be multiples of it. So we're going to find two different ways of finding that fundamental frequency. And the first of them is experimental. The experimental way is we'll just do it by observation. We're going to have a wave set up and we're going to observe different waves on it. And so we're going to calculate the fundamental frequency by taking the frequency that we find each of those numbers and dividing it by that number. So in other words, we're going to take the frequency which we find 3 loops and divide it by 3. Frequency 4 loops divided by 4. Those are going to be our experimental measurements of the fundamental frequency. For the theory, we need to go back to here and we need to know what the theoretical value for the velocity on a string is. the velocity on the waves on a string is equal to, theoretically, so if you think about the spring lab that we did, remember the spring lab had the period being the 2 pi square root of k over m. In other words, k is kind of the force of the spring. It would tend to make it go faster. The mass, of course, of the spring would tend to make it go slower. So in this case, we have sort of that. But first of all, we're talking about the forces of a string, not a spring. So what kind of force do we have in a string? I take a string, and I want to put force on it. What force is in that string? There we go. Good job, Kobe. So that string has a force of tension. And so that's what we're going to put here. This is capital T for tension. Now, the problem, of course, is the mass of the string. I could just pick more string if I wanted more mass, but we wanted to have something to kind of describe the thickness of the string. So that's where we use this mu quantity. Mu. That's a Greek letter. So physics has gotten, by the end of 100A, you start getting really more complicated physics. We run out of American letters and we have to use the Greek ones. All right, so this mu is the mass per length of the string. Now, I'm going to write this down as we do in our data tables. Lowercase letter m divided by lowercase letter l. Because these are different from what we have up here. Huh? Yeah, this mu, we're going to set what the tension is, and this mu depends on the string itself. So that's not going to change for our different waves. Okay, so that's the mu. So let me draw that mu up here. So the mu is equal to lowercase letter m divided by lowercase letter l. And the tension, how would we calculate the tension? Well, the tension is being produced by this capital letter M, by that mass. And the tension is going to be the weight of that. So this is just equal to capital M times what? G. I wonder what it is.
Gravity?
Yes. G. I wonder how you got that. Tried to give myself a rim shot there. So that was really bad.
Professor,
All right, so,
is there no data sheet for this lab?
Data sheet. Well, we haven't started taking data yet, but yes, there's a data sheet.
I don't see it posted on Canvas.
It's not posted.
Oh, okay.
It's not posted because of the snafu that I had over the weekend when they turned off my internet in here, so I couldn't post anything. So I'm just barely recovering now from that. So the data sheet is page 61 in the back of your lab manuals.
Okay.
Okay. So at least one person from each person will have to tear that out. So, all right.